Our next speaker is going to be Tobias Grosser. He's going to be telling us about the code generation, more general code generation of loops. So this is work done with Sven Bergowitz and Albert Cohen. Apparently this is the Albert show.
Hello. All right, let's see if that works. All right, so let's get going. Yeah, I'm Tobias Grosser. I'm a DT from ETH2. And so in the next 25 minutes, I try to convince you why polyhedral AST generation is so much more than integer scanning of polyhedra. So this is joint work, and in fact this is research work we did over at least 5 years. So Sven Bergowitz started very early on this topic, and it's research work where we started with existing polyhedral AST generators, where we got blocked by limitations, where we tried to understand how it works, and where over time we didn't only address the limitations, but what I think is we actually expanded polyhedral AST generation to something which is, yeah, maybe not always considered polyhedral AST generation before. So the result is an entirely new AST generator, and I have the honor to present this AST generator to you. So let me first tell you that polyhedral AST generation is really at the heart of not all of research, but there's at least a sufficient number of research projects that use polyhedral AST generation. You just saw a presentation that is using such techniques. There are different other techniques, so there's Polymage, which is a DSL for image processing kernels. There's Pluto, a very well-known PLDI paper about deriving, or it's a like very general purpose loop optimizer for data locality and parallelism. There was just recently at CGO, there was a new paper based on the original ideas of Spiral to derive a code generator for basic structured linear algebra. We had a PLDI paper on exploiting associativity to reduce register pressure and memory I/O bandwidth for stencils. I work on a polyhedral loop optimizer for LVM, which is using a lot of such techniques. And another paper I've been part of is a paper on hybrid hexagonal tiling, which uses an advanced tiling scheme to generate efficient GPU code for stencils. So now let me wake you up with a picture and explain you briefly hybrid hexagonal tiling. So I know most of you know stencils, and I know most of you know what tiling is, so probably all of you understand why this tiling scheme is very good for GPUs, right? So everybody who is not up to date, what you need to do for a GPU is you want to optimize for multiple levels of parallelism, coarse-grained parallelism, fine-grained parallelism. You want to provide sufficient levels of parallelism at all levels. You want to ensure there is memory parallelism when you read from memory, there's no thread divergence, and you want to take advantage of shared memory on your GPU. And so this tiling scheme provides this by providing hexagonal tiles on one dimension and classical tiling on other dimensions. And this tiling scheme is actually very difficult to generate code for. And there are multiple reasons for that. So one reason is that, well, that's a solution to partially, but so one reason is that just to define such a tiling scheme, you can't just use normal rectangular tiles, but you really have to define such kind of hexagons, which requires you to use some kind of Pressburger arithmetic to even define the tiling. The second complication is that you want to do a memory mapping, and to define a memory mapping that actually precisely copies the data, you can't just copy a rectangular set of data because, well, the tiles are not rectangular, so the data you need to copy is not rectangular. And if you would copy a rectangular, you may overwrite data that you need later on. So let's focus just on the copy out code of this tile. And this is the copy out code we would generate to copy the data computed by one of the tiles. So you don't know the input, you just know the output. And I'm not claiming that the output we generate for our copy code is optimal. But I'm claiming that it's at least non-trivial to generate a lot better code for such kind of tiling pattern. And some of the complications you can see in the code. So here, for example, we have a modulo 128, which is because we apply some kind of modulo mapping to map from the global memory to the actual local tile. The second thing is that we have a lot of conditions here, specifically to match the pattern of this hexagon. And now the question is, this is a big step ahead because we can generate code for that. But still, that doesn't run fast. And so one way to make this faster is to unroll the loop. And this seems to be very trivial, because the result is actually pretty trivial. It's just a straight line sequence of instructions, and a couple of them are predicated. So this is the code you actually run on the GPU, and this is really fast. Now, to actually generate the code, if you give the original unrolled code to your compiler, you'll figure out that your compiler can't actually do anything, because it has no idea how often this loop is executed, just because, well, the code is becoming very complex. And the good thing is, in a polyhedral AST generator, we actually have the context knowledge to do such kind of predicated unrolling and generate efficient code. The next thing is that you see the index expressions, they didn't get a lot simpler, but in fact a lot of forward propagation happened. So index expression, also thanks to the context knowledge, got a lot simpler. Now I gave you an introduction without explaining you what all the background is. So let me very briefly tell you what actually the background model is that we have. So we work on loops that have static control, so lower and upper bounds are not data dependent. And if you now would just execute this loop mentally, you see that all the loop bodies, the individual instances of the loop body, can be enumerated. And they can be modeled in a multidimensional iteration space. And this multidimensional iteration space just corresponds, the dimensions of this iteration space just correspond to the individual loop iterators. And this is very nice because we can now place all those statement instances in our iteration space. And what you see is that the set of statement instances can be concisely and precisely described by a set of integer affine inequalities. And this can be described by a Pressburger set. So we now have a mathematical, geometrical model of our computation, which was the origin of this later, a lot more complicated hyperhexagon tiling, right? Now, assuming there's a lot of interesting, crazy translations, optimizations we could do in this geometrical model, what we focus on here is really just the AST generation. And to get back from this iteration space, there's only one thing we need. And this is, we call it a schedule. It's a mapping that from each individual statement instance that is executed, maps each statement instance to a multi-dimensional time where the statement instance is supposed to be executed. And this schedule defines the execution order of our new imperative AST. Now, to actually obtain this AST, we start off very simple. We just switch the schedule. So from schedule turns into an executed relation. And this executed relation tells us at which time step, which statement instance is executed. And now the question is, how do we generate code? So this one says basic example, so it's really simple. Yeah, so it's very simple. And it really starts off, you just project on the prefixes of those, this scheduled or time dimension, time space. And so we project on the I dimension, and we immediately get, just by the projection, constraints on I. In this case, it's very simple because there's only one lower and one upper bound. So we can immediately generate a for loop for this set of constraints. All right? So now projecting on the second two dimensions, we get two new constraints, and we could again generate a new loop going from 0 to 2. In this case, we happen to be in a special case because all the numbers are matched to exactly one statement, so we can immediately generate the statements that correspond to the numbers, and two of them are fully scheduled. And the last statement that we lack still has an additional dimension in our schedule space, so we project now on all the three dimensions, and we get constraints on J. And here we have a very simple loop, code generated with AST generation techniques. Obviously, in reality, it's a lot more complicated. So let's start with one case that is more complicated. And this is a case where we actually have existentially quantified variables. So I didn't formally introduce this, but the domain that describes here the iteration space, it's a Pressburger set. So this is a Pressburger formula on the right side. And the interesting part here is that here, on the left, you have an existentially quantified variable. And it's, well, if you actually want to generate the constraints for the set, you need to get rid of this existentially quantified variable. So there are two different approaches. The first approach is that you use quantifier elimination. So instead of having this existentially quantified variable, you introduce multiple convex polyhedra. So instead of having one convex polyhedra with an existentially quantified variable, now you have multiple. And each of them has bounds on the variable you currently want to co-generate, and so you get 2 for loops to enumerate this set. The alternative is that you use Fourier-Motzkin, which is a rational approximation or a rational quantifier elimination. And here the code is a lot simpler, or in fact you just get one loop body, but it's an approximation. So this becomes clear if we look at the iteration space and an illustration of the iteration space. And you'll see here that there are 2 additional points by Fourier-Motzkin, which we just by using quantifier elimination do not get. Now, we have two solutions for one problem, and so when do we want to pick which solution? And obviously we want to go for code as simple as possible, so we will use Fourier-Motzkin for all the outer loops. But at some point, it's very insatisfying if we over-approximate our program because we do too much work and most likely we access some memory we don't want to access. So at the innermost level, we actually need to do quantifier elimination to be able to handle the full complexity of Pressburger arithmetic. But in the best case, we never reach this inner level with our existentially quantified variables. And yeah, but if we do, we support that, and you can generate code for that. Now let me go to a second example. So this talk is mostly by example because I think the paper is too long to explain every detail, but I picked really out the interesting examples. And the next example is if you want to unroll this loop. So this loop is defined, this might for example be a tiling, that you have a large iteration space going from 0 to 1000, and at the same time this iteration space might be constrained by a smaller tile set. So you're not fully sure where the tile starts and ends, but you know that it's small. So now we want to unroll this code. What are the complications we see here when unrolling this code? There are 2 decisions we need to take. And the first decision we need to take is, where do we start unrolling this code? Do we want to unroll the code starting from 0? So I equals 0, I equals 1. Or do we want to start unrolling the code at n? N equals I equals n, I equals n plus 1. Both would be a valid unrolling. One would be a little bit more clever than the other, right? Because if we start unrolling at 0, we need to unroll a lot, potentially 1000 times. And this is exactly why we have 2 choices. So there are 2 lower bounds, and depending which bound you choose, you either get very complex code, or at least very long code, or very concise code. And so figuring out what is the right bound to unroll, and then deriving this conditional, so because the interesting thing is we are not actually doing unrolling, we do this conditional unrolling. So deriving the set of conditions necessary to, conditions for each conditionally unrolled statement, instance, yeah, however, is a second interesting question. Now, let's see one other question. So if you want to vectorize a code, if you want to tile a code, a very common optimization is to specialize computation. So we see large speedups from that in our hybrid hexagonal tiling, but it's in general very applicable. You have a core computation which should run very fast, and then you have all the boundary cases which should be correct, but they may need a lot more conditional code to actually be correctly executed. And so if you partition the space and generate specialized code for each of those 2 instances, the code may be potentially a lot faster. And so in this simple example, we just have one loop going from m to n, and we want to assume we want to have a polyhedral way to vectorization. So the polyhedral way to do vectorization is we strip mine the loop, generate an innermost trivially vectorizable loop that has only 4 iterations, and then map this innermost loop to a vector instruction. Now if you actually want to do that, the vector instruction you need is pretty complicated. It needs to be predicated in some way because it's at most 4 iterations, but it might be less. And so a way to exploit this, or to simplify the code generation here is to use this isolation and specify an isolation constraint that tells us what is the core computation and what is the boundary. And then the IST generator takes care of generating a nice core computation. So this is the loop we are interested in. It starts at 0, it has 4 iterations, and this is the one we can nicely map. And all the other before, after, other code, it's never executed except at the boundary. So this is just needed for correctness. It looks a little complicated. Depending which tiling scheme you use, it is complicated. So if you just do vectorization, it's very trivial. You just can generate this manually. You write a pattern and generate code for that. If I would ask you what is the before loop for my hypertextual tiling? Anybody knows how that looks like? I honestly myself have no idea. I would not generate that, but I don't need to, so it's okay. And then the next thing I want to point out is AST expression generation. So instead of just generating control flow, very often you have a problem we just recently saw. It's interesting to change the memory layout to do data mapping. And very often if you do that, what you have is you have the original data location, and then you map a big piece of data to a smaller set of shared or software managed memory. And very often you can do this with some kind of modular mapping, which we also just have seen. And if you actually just try to generate code for a straightforward modular mapping, you'll figure out that C, unfortunately, has slightly different semantics to the mathematical modulo I'm using normally. And so instead of just using C modulo, you just use this floor division marker, which is conditional on the signedness of your value. You figure out that you actually need to do a lot of computation, for example, to do a division or modulo. And so, interestingly, in most cases that's not necessary. So it's actually very simple observation that if you can prove that I, in this case, is larger than 0, or larger equals 0, we can simplify this to an actual C division. The same if I is known to be negative or 0, if we know that it's a multiple of 4, we can always simplify this. And in this case, the context constraints here look very, very simple. But in practice, imagine again you have this big hypertextual code, and at some point you have an expression where you need to know what is the signedness of this expression. For a compiler, it's almost impossible to derive. But if you have the full context available, you can, in the worst case, just build a little optimization problem and ask what's the minimal value, and you might figure out that it's large enough. And in this case, you can simplify such kind of expressions. Let me move to a slightly different, but also I think a very useful part of the code generator. So even if you didn't work on polyhedral code generation, you may already have gotten a little bit confused by the way we represent scalars, just as a affine relation between input and output specs. A lot of programmers, a lot of compiler writers are a lot more prefer to work more on tree structures because it's a lot more easier to reason about tree structures. And in fact, a lot of transformations and a lot of programs look like trees. So we introduced some new scalar representation, which we call scalar tree. And so here it has at the beginning the iteration domain, which I introduced on the simple example. Here it's slightly more complicated. We have 2 statements. We have more loop iterations. And here we have a schedule now also for 2 statements. Here at the beginning we had the loop that iterated from 0, 1, and 2. So now we make it explicit that this is actually a sequence. And again we have a construct to add constraints without having them to be part in our schedule. So it makes a lot of the nodes in our AST generation a lot more straightforward. And so this is nice for a programmer, but in fact it's also nice for the AST generator because it's a lot faster. If for any kind of AST generation you need to solve ILP problems, optimization problems, this is a lot slower than actually reading off code generation from a tree. Now let me just show this very briefly in practice. We have on the left side a schedule tree, on the right side the code. Now we just apply a simple sequence of transformations. We do tiling, we do split the bands, we do some interchange, strip mining, we again do some isolation of core computation. And what you see, a slightly more complicated example, and we again have our trivially vectorizable loop. So again, we did this isolation, this time on a schedule tree. It looks a little bit, the program is bigger, but I think the configuration and the implementation on a schedule tree is probably a lot more straightforward. Now, we are done with some of interesting parts from our AST generator. Let me now go into the experimental evaluation what we did. So the first part, I don't even write any graphs, so this thing is robust. We have it in GCC and in LVM. We use it for a lot of our research. And in fact, we also proved for a lot of our test cases that they are correct by mathematically checking that the output of our AST generator actually matches with the input we gave it. So this I think it's a robust thing. Now, let me We also looked into code generation performance, and here we had to compare with a couple of previous existing tools. So for this very specific example, we compared against CodeGen Plus, which was a recent, is a recent AST generator. It does not support the same, or not everything we are doing, but it also has basic support for existentially quantified variables. And so here we just used Polybench as a simple benchmark of, I would say, the classical AST generation problems. And here what you see is that you don't see anything. So any point on this diagonal means that both AST generators are giving you the same performance. So for a lot of test cases, we really see there's not a lot of thing you can gain just by, like for the classical AST generation problems. Now, there were a couple of test cases we looked at where we actually got better performance. So here we see 1, 2, 3, 4 test cases where we were a little better. This is interesting because the way we actually illustrate the improvements, we chose this way because really depending on the compiler, one AST generator may be better and the other one not, or the other way around. So here you will see that we are for all 3 compilers, we are actually better for those test cases, and CodeGen Plus is a little better for ICC for a couple of test cases. But this basically says that for classical AST generation, there's nothing to be gained by our AST generator. Still, I think I'd like to report this for completeness, and for bigger programs, there's probably something interesting to see. Now, let's look at some selected examples that show off some of the differences. So this is what Club generates for one test case. This is what CodeGen Plus generates, and this is what we generate. And so what you see here is that there's, for a lot of previous AST generation approaches, there's at least some code duplication, unnecessary code duplication, which we prevent here by an optimization we call component optimization. So I didn't discuss this in detail before. And the CodeGen Plus has a lot of conditions in its control flow. Now, if we actually run this, and by running I mean simulating it in Valgrind, because yeah, as we saw, the performance results are very different on different platforms. So the most precise I can give you is a dynamic instruction count. And we see that for this test case, even though the code can be a lot simpler by ISL, so we have here ISL, we have CodeGen Plus, and then we have a third code generator. This is Cedric Bastous's work called Club. And so here we see that we can reduce the code size depending on the compiler, but the performance to solve this code size increase didn't really change performance too much. Now for this test case, this is simple. This is another technique I actually did not explain. But what we see here is that often you have some strided iteration pattern. So you jump in strides of 2, for example, here. And for the input code here, we see that Gluck actually has to generate if conditions to implement this striding. And as a CodeGen understand that we can actually choose a bigger stride. So instead of 2, we choose 4, and then we can drop the if conditions out of our control code. And this has very nice impact in dynamic instruction count because we can really more than half the number of instructions executed. But interestingly, for ICC, we get a huge increase in code size. A lot larger than what you actually would expect. And so this is again interesting because it also showcases that, well, a lot what you do actually very much depends on the compiler. So now the question is, why is ICC generating a lot larger code? And the reason is because our code is simple. So ICC is unrolling this code, it's vectorizing this code, it's doing a lot of stuff on this code. And if you disable all this stuff, we are again in the normal code size range of all the other optimizations. But this is one point where you say, okay, it looks nicer to a human being, but it may also look nicer for your compiler, so it may actually enable a lot of backend compiler optimizations. Another thing is the modulos. So CodeGen Plus is generating modulos for simple modulos, it's generating those loops. We just generate individual statements and we can recover the modulo here. Here also to realize, we recognize that this is a C modulo we can use, just because we can prove that n is positive or non-negative. If you look at the instruction count, you see we again, so this is log scale, we get both a reduction in dynamic instruction count, added code size. So if your code uses a lot of modulo stuff, so it's a non-trivial tiling, I think this is very useful. The same for unrolling. Those are two interesting cases. The first is, well, 2 loops that need to be unrolled. The first goes from 0 to 7, and the other loop goes from something complicated to something complicated. Both look a lot simpler if you unroll them. Now if you look at the dynamic instruction count, what you see is that for the different compilers, for the first test case, we don't get any difference, or any notable difference. And the reason is that the loop goes from 0 to 7, so it's small enough for the compiler to unroll, and when it starts unrolling, we don't need polyhedra unrolling. For the second test case, we see that this is very complicated for the compiler, so it doesn't do anything, and we get a huge order of magnitude decrease in the number of dynamic instructions executed, and as well in the code size. Now, our very last evaluation was actually our hypertextual tiling. So here we look at the performance on my laptop, so it's not HPC, it's just my laptop, but it's good enough for this AST generator. And we see that if we use the same tiling scheme without any of our advanced transformations, we get around 2.5 gigaflops performance. And if you enable all the optimizations, we are around 28 gigaflops for both a 2D and a 3D stencil kernel, which is pretty good for this kind of kernel on my machine. And now what you see is that, for example, our isolation, our full partial type separation, gives us around close to 5 gigaflops more performance. Unrolling is super helpful, so it gives us between 20 to 10 gigaflops of performance compared to our best performing code. And modular detection, for this test case, it doesn't give so much performance because, well, obviously, if you can get rid of the very complex things, it's a lot better. But this modular detection, if the code is already good and you can get another 2-3 gigaflops, it's still very nice. Now, let me conclude. We have a new AST generation approach, which I think goes far beyond behavioral scanning. It has complete support for press-program relations, which previous approaches did not have. It supports any kind of existentially quantified variables. It supports piecewise schedules, and it has facilities to aggressively simplify the AST and AST expressions. It has support for stride and component detection. It has, I didn't mention this, but I mentioned it in the conclusion slide. So a lot of the choices you have during AST generation, it's not just an on and off flag, but you can, for a specific subset of your schedule tree, you take different decisions, options of your code generator. So you can one part optimize for minimal code set and the other part for minimizing control. We allow specialization, both polyhedra unrolling and user-directed versioning, isolation, and we can generate AST structures, ASTs for structured schedules. So, before concluding, I want to point you to this website. I hope it's updated. So this is probably not accessible with this network, but if you're at home, this has a Python implementation compiled to JavaScript. So there in the web browser, you can just try our AST generator and generate a couple of simple ASTs. That's all. Thanks for listening. I'm happy to take questions.
Questions?
Hi, I'm Nimit. I'm from UPenn. So my question is that do you have any correctness guarantees about the code generated? As in, like, can you ensure that semantically the intended code is generated, and if not, then what?
No, we cannot. No. What I can tell you is that assuming the correct, there are two things about correctness. One thing is that we have a tool that allows us for the majority of the schedules you can provide to actually compare the input with the output and see if the AST generator did the right thing. So we can't prove it ahead of time, but for a given example, we can tell you if it did the right thing or not. And the second thing is, so now assuming you believe us whatever we do is correct, we can actually verify if the schedule you give is a valid transformation. We just use classical polyhedral modeling techniques and verify if the schedule is correct. So you can say, assuming the infrastructure is correct, I myself can check limit my correctness check to just checking if the schedules I generate are correct.
Okay.
Yeah. 2 pieces not complete correctness, but they may still be helpful. Okay.
So following on the previous talk, where there was discussion about various storage optimizations, that's going to change the memory accesses, the array accesses. So you were mostly focused in this talk on the schedule. How do you envision the code generation when we're changing the storage allocation? How's that going to work with this work?
Okay, yeah, this was one of the things that I think very nicely described in the paper. I didn't mention them too much here, but so I briefly mentioned, let me go back here, that it's sometimes useful to detect modulus here. And in fact, we provide facilities not just to generate a control flow from a schedule, but in fact to take an arbitrary piecewise affine expression and generate an optimized index expression for a given storage transformation or storage layout, for example. So if you can express your storage transformation as transformations or as piecewise affine expressions, we could help you generate code for that. And the nice thing about this AST generator is that we can actually combine this. So if you generate a full AST, and at some point you end up at a statement, at this point you have a lot of context information. And you can pass on this context information to your memory layout transformation, for example. And this can help you to simplify the code you're generating. So one example of this is this full partial tile separation, for example, in stencils. Stencils often have boundary conditions. Now if you implement a code generator, well, implement a stencil compiler using this code generator, you perform full partial tile separation, and you express the index expressions using this piecewise affine expressions. At the time you generate code for your core computation, you will have the context that the boundary doesn't happen. So at this time you can specialize your access expression, and the hot code is actually simpler than it would be otherwise.
Great. Thank you very much.
All right.